This is Jack Jackson. We're going to be looking today at inverse trigonometric functions. This video is going to introduce us to the concept and talk about the arcsine or inverse sine function, and we'll follow this up with videos for each of the other 5 inverse trig functions. So first of all, let's just recall what we mean by an inverse relation. So given any relation, its inverse relation is found by reversing all its ordered pairs. So for example, if 2, 3 is an element or a part of a relation, then 3, 2 is going to be a part of its inverse relation. So 2, 3 is in the table for one relation, then 3, 2 is going to be in there for its inverse relation. So notice they come in pairs. So we're just reversing every ordered pair in the table. So if we write out a formula with x and y, we change x's to y and y's to x's. So replace x by y and y by x to find the inverse relation. The inputs and outputs then will switch roles. So an inverse relation switches the role of input and output. And so that means the domain and range will switch. If you have a relation where the input is the day and the output is the high temperature, then the one that has the input, the high temperature, and the output today will be the inverse relation. If you think of it as a series of steps, you're performing the opposite steps in the opposite order. If we think about it as a graph in x and y on a Cartesian coordinate plane, then the inverse graph will be a reflection of the original relation graph reflected over the line y equals x. So any graph, if part of the relation touches the line y equals x, then those points will be fixed and they'll also be on the inverse relation. So every relation has an inverse relation, but it may be true that they're either both functions, or one's a function, the other one's not, or vice versa, or they're both not functions. So which ones are they both functions? Well, it turns out that the only ones that are both functions are the one-to-one functions. Sometimes that's called injective functions. Okay, so there has to be a one-to-one function to be an inverse, to be both of them be functions, both the original function and its inverse relation to be a function as well. So notice if the original function, say, passes a vertical line test on the graph, that makes it a function. That means its inverse will pass the horizontal line test. Well, if the inverse is a function, it passes the vertical line test, which meant the original passed the horizontal line test. So the only way for them both to be functions is to pass the vertical and horizontal line test, that they're one-to-one functions. In other words, every input gives you only one output. That makes it a function. But in addition, every output only comes from one input, and that makes it one-to-one. Well, notice that trig functions are definitely not one-to-one functions. They're periodic. So their inverses are not going to be functions. Okay, so I have actually infinitely many inputs producing the same output for every valid output there is. So the inverses, the trig functions, are not functions. But we have things that we call inverse trig functions. Okay, and so they're not really inverses of the basic trig functions. What they are instead are inverses of the original trigonometric functions restricted to a smaller domain. So basically you take the original trig function, you throw out duplications basically, so that you keep every y value once. And of course there are lots of different ways to do this, but we want to do this so that we keep a portion that's in the original domain is either, we keep the portion of the function that's between negative pi over 2 and pi over 2 in some cases, or we keep the portion that's between 0 or pi, whichever one will make the function one-to-one, and it will not change the range. So we'll keep all the y values exactly once, throw out the rest. Then we have a one-to-one function, and that function, which is part of one of the trig functions, then we'll take its inverse, and that'll be the inverse trig function. Okay, so the inverse trig functions then will be one-to-one functions as well. So inverse trig functions are one-to-one, Regular trig functions are not one-to-one. They're periodic, definitely infinitely many things going to one, but their restrictions will be one-to-one, and that's what we take the inverses of. Also in red down here, notice use Radian mode anytime you're graphing any trigonometric or inverse trigonometric function. So be sure that you always put your graphing calculator in Radian mode for any of the things that we're doing with graphs. So now I'm going to click right up here, and it's going to, where it says introduction, it's going to hide that introduction. I'm going to turn on the axes. If I want a coordinate grid, I can turn it on, but I don't have to. Of course, this is coming from my sketch Trigonometry Ultimate, which I've been using for this class, and we're in Unit 3, and this is inverse trig. So I'm just going to turn the axes on, and I'm not going to worry about the grid. We can turn that on later if we want. Okay, so I'm going to start with Arcsine for this one. If I click on definition, this goes through the process right here. Okay. So, and you can click on these buttons here to turn on the axes and the coordinate system. If we want the coordinate system on, we're definitely going to need the axes. And notice I have a trigonometric kind of scale so that the x-axis is marked off in multiples of pi over 4. So that's pi over 4. 2 pi over 4 is pi over 12. 3 pi over 4, pi, which is 4 pi over 4, and so forth. And so these are the x coordinates, and then the y coordinates are going up and down here. Okay, and so there's our scale, and we just have a regular 1, 2, 3 scale, but it is a square scale. So this button where it says scale, that's actually at 1, 0. So that distance from the yellow to the green dot is the same as from the yellow to the 1 up here, and I can I can zoom out or zoom in as needed. So let's just say we leave it right there. Okay, now let's graph y equals sine of x. So there's our good friend y equals sine of x. Notice that it is domain is all reals. Range is from -1 to 1, but that range, elements in that range get used over and over and over and over and over and over again. So if we put the line y equals x on here, and then we reflect this, so if we just take our formula and change this y to x and that x to y, and then we have x equals sine of y, and there's the graph of x equals sine of y. Notice it's flipped over. The original sine of x is flipped over the line y equals x to get a reflection there. And that is y equals sine of x. And just as sine of x is a wave that's kind of centered up on the x-axis, that's y equals sine of x, then x equals sine of y is a wave that is centered up on the y-axis, like that. And so, well, definitely that's not a function. We want our inverse function, our inverse sine function, to really be a function. So we're going to only take part of this. So what we need to do is we need to take the sine wave here, and we want to pick part of it. Now, we would like to include the origin, so we're going to include that. And we're going to include this. We definitely want to include these things that correspond to acute angles on the unit circle. So we're going to include this part between 0 and pi over 2. If we started to go over here, we would be doubling up y's, and we wouldn't get our goal of 1 to 1. But if we go this direction, we can still keep it connected. So what we're going to do is we're going to keep this part from negative pi over 2 to pi over 2. And that is this restricted sine wave. So notice if we just keep that part only, okay, then we get a graph of the sine function, but only part of the sine function. Now, if we just look at that part there, we see that that is a 1-to-1 function. Where does it go? It goes from negative pi over 2 to pi over 2 on x, and from y goes from negative 1 to 1. We can maybe look at something there. Okay. Now, if we take that function and reflect it over the line y equals x, that gives us our arc sine function, or inverse sine function. Okay, so the red one there, and notice that's part of x equals sine y, but it's not all possibilities for x equals sine y. It's the only possibilities for x equals sine y where y is between negative pi over 2 and pi over 2. And these reference lines here can help a little bit. This one down here, this is when y is negative pi over 2. Of course, you got y 0 here, right in the middle. This is y equals pi over 2, and there's another reference line we might need later for y equals pi. Okay, and then horizontally, this is at 1, and this is at negative 1. So, what are these points here? What's this point right here on the sine graph? Well, it's x equals pi over 2 and y equals 1. So what's the corresponding point on the inverse? It's going to be right here, and that is, we switch the ordered pairs, that's going to be 1 comma pi over 2. This one here on the sine, restricted sine wave, was pi over 2 comma 1. Its image is over here, 1 pi over 2. Now, if I look at this and put a line segment across here, notice that that point right there on the line y equals x is the midpoint of that line, and notice we have a right angle. We have a right angle right here. Oops, not there. Okay. Alright, so let me hide that. And that's what it means to be a reflection, by the way, over a line, is that when you connect up the pre-image to the image point, the reflection line, the mirror line, is going to be the perpendicular bisector of that line. So it's going to be meet at a right angle, and that's going to go through the midpoint. So you can kind of see it on that point. And you could match up any corresponding points on this, and that would give you it. So what's this point down here? Well, the one on the x, y equals sine of x, the original one, okay, is negative pi over 2 comma 1, negative 1, and so this end point on the arcsine is negative 1 comma negative pi over 2. So again, that's part of x equals sine y, but only the part to make it a one-to-one function, just like the sine wave. It's not a reflection over the line of y equals x of the whole sine wave, but only on just the part where that we keep. And what part do we keep? We keep this part right here in blue, and that's going to be from negative pi over 2 to pi over 2. So ultimately, this is what's left. Actually, let's look at this, and let's zoom in on just this part a bit. Okay, and there we go. Now we can see what's happening there with the shape. Okay, so let me close out that definition, and let's look at some properties that we might notice here. So, what is the domain of the arcsine function? Okay, well, the domain is the set of all first coordinates, and it's the same as the range on the sine function, which is negative 1 to 1. Okay, the range of this is going to be the same as the domain of the restricted version of the sine function, which is from minus pi over 2 to pi over 2, and we can see that down here. So y goes from negative pi over 2 at this point, and it actually increases the whole way to this one up here at y equals pi over 2. And it goes through the origin. So the x and the y intercept is the origin right there. And it has these endpoints at negative 1, negative pi over 2, and positive 1, positive pi over 2. Notice that it is a continuous increasing function. The origin is also an inflection point because this part down here in the third quadrant is concave down, and the part up here in the first quadrant is concave up. Okay? Now when I said third quadrant and first quadrant, I'm talking about of this graph, not of the unit circle picture. Okay, so this is a continuous, increasing one-to-one function. Concave down for x is going from negative pi over 2 to 0. Concave up from 0 to pi over 2. The output y can be thought of as a measure. Of course, over here it's just a y value, but we can think of it over here on the unit circle as the output being some angle between a rotation of negative pi over 2 this way and a rotation of positive pi over 2 inclusive. So something like this. Over in this picture, the output is a first or fourth quadrant angle, specifically one between negative pi over 2 and pi over 2. Okay? And let's see what else. Okay, one more thing that I want to show you before we leave this is there are different notations for it. You can see those notations right here. Okay? Really the preferable notation is arcsine of x for this. That's Arcsine of x. But another very common notation is sine superscript -1 of x. So you might read that as inverse sine. Sometimes you'll also see it as INV-SIN or A-sine. In Graphmatica, for example, you type in A-sine, this last one. These last two are not so often used. The first two are pretty common, and the second one with the sign with a looks like a -1 exponent, but it's not an exponent. That one is very common, and it's used on your calculator. So I will use that one quite a bit, just because it's on your calculator, even though I prefer to use just arcsine. And one of the reasons why I don't like the -1 superscript is if it was any other number, if I say sine to the n of x, this means take sine of x and then take that whole quantity and raise it to the n, and this works for any n that's not -1. But sine -1 of x does not mean sine of x to the -1 power. What is sine of x to the -1 power? Well, that's 1 over sine of x, which we would write as cosecant of x. So these are the same. This is the arcsine of x. And of course, those are two very different things. But unfortunately, this notation looks like, like sine squared or sine cubed. So I prefer arcsine, but this notation is very, very commonly used, particularly on your calculator. So of course, this is the arcsine function. Here is just the cosecant function, and those are extremely different looking graphs. Not even close. Okay, so that gives us an introduction to inverse trig functions in general, and specifically the arcsine function. And then we'll come back in our subsequent video and follow that up with a shorter video on just each of the other inverse trig functions.